Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is Rhino Grasshopper integration in RFEM 6. My name is Amy Heilig. I will be your moderator today, answering any questions you may have. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. I'm also joined by my colleague, Siska Choa, who will be also a moderator today. She's a technical support engineer. And lastly, Alex Bacon, who will be our presenter. He's a technical support engineer, also located in Philadelphia, Pennsylvania. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. And if by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. And with that said, I'll go ahead and turn it over to my colleague, Alex.
Great, thank you, Amy, for that introduction. So regarding the content for the next hour for today, first I would like to start off with going over some general information. And then the next bit of information will be the data exchange between Rhino and RFEM 6. And then I would like to end with the data exchange between Grasshopper and RFEM 6. So first I would like to start with some requirements and installation information. The first important step is to install the Rhino plugin, and this must be done manually. And this is different from previous versions, so it's pretty easy. You just need the full version of RFEM 6 or the trial version of RFEM 6 installed, and then you just need to locate the file delubal rfm6 plugin.rhi at this file location shown here, and then just run the file here to install it. So most programs communicate directly with each other. RFM5 used to use the COM add-on to do this, but recently with the newest version of RFM6, we replaced this with the web services. So at the moment, it is required to have the web services license purchased to use this direct interface. In the future, we do plan to remove this requirement, and every direct interface made by us, for example, soon Tekla and Revit, will not need this license. So if you would like to test or use this right now, just email us and we can set you up with a web services license. Then you need to start the server to use web services. It's pretty easy. All you need to do is go under the program options and settings in RFEM 6 and make sure this option here is checked on, and then the plugin will be ready for use once you open up RFEM 6. Next, let's go over a rough overview of the plugin itself. So the Rhino plugin, Rhino Grasshopper plugin, is actually made up of two plugins. The first is the Rhino RFEM link, which is pretty similar to the past. So with this link, basically you have the options to import and export and this transfer simple geometry like lines and surfaces. Materials and sections are not included with this transfer, and so we did improve on this a little bit. And the other link is the Grasshopper RFM link, and we have a little bit of more changes when it comes to this link. So mainly the export, but now you are also able to import as well. And then you are able to control aspects like model data and supports. And when it comes to the export, you have more control over the structural analysis. Additionally, low cases and combinations can be accounted for, which was a big request from our users, along with loads. As a side note, not all loads or every feature can be controlled by Grasshopper. We tried to pick the most common ones, and so if we are missing something, please let us know. It's pretty simple for us to add additional features in general. So now, for those who might not be too familiar with what I'm talking about, I would like to go over the workflow. So in general, Rhino and Grasshopper in combination with the Dulubo plugin is an alternative method for model generation. So instead of using RFEM6 to generate the structure, you can use Rhino and Grasshopper to generate the structure and generate lines/services based on algorithms. So this is more like programming instead of drawing. And in those algorithms, you can assign parameters to a structure, and then you can, at the end, just enter in parameters and use the doable components to assign additional info like cross sections, materials, eccentricities, and thicknesses. At the end, you get a structural analysis model in RFEM6 that you can analyze and design there. And then the results can be compiled and visualized into documentation in RFEM. And what we recently just implemented is the option to import back into Grasshopper. And this lets you read the results from the analysis in RFEM6 back into Grasshopper. So with those results, you could run additional optimization routines or use them to visualize the data. So with that said, now let's start with looking at the simple plugin between Rhino and RFEM6. So I'm just going to open up Rhino here on the right-hand side and RFEM6, Rhino on the left-hand side and RFEM6 on the right-hand side. And you can see on the left-hand side here, I have a small Rhino structure that consists of surfaces and lines. So I have my surfaces here, and then I have my beams, which are also made out of surfaces. So for example, if I click on the details here for my beam, you can see that it's made out of NURB surfaces. I also have defined here some layers. So I have my roof layer, which I can turn on and off, my diagonals, and then also my beams. So now let's say we would like to export this model into RFEM6. So after the installation of the plugins, you should see up in the top here a tab for RFEM6 with two buttons included inside of it, the export button and the import button. And if I click on the export button here, you have a couple of additional options and settings you can change around. So first setting is you can overwrite a model. So with this option, everything in RFEM will be deleted and the new model data will be transferred over, or requested by our customers is the append option, which keeps the data previously defined in RFEM. I'm going to keep this set to overwrite, and the next option is the ability to flip the global z-axis. I'm going to keep this unchecked. And then you can also add in a shift offset. Keep in mind these values for the shift offset are related to what's defined in Rhino. The last bit of options here are for selecting layers that we want to export. You can also just export objects that you have highlighted in the model in the background. And also hidden objects will not be exported, and that's not an additional check you need to worry about. So what we'll do here is we'll just select our roof layer and our diagonals to be exported. And then we're also going to keep this option to use layer identities checked. And what this will do is create visibilities in RFEM using layer names. So before I click OK, I also wanted to point out in RFEM6 here, under options and program options, and then scrolling down, this is where you can check on the option to have the server for web services start automatically with the application. So you have to make sure this option is checked as well. And so now I can click OK to begin the export process. You'll see up in the top here in Rhino, you'll get some statuses in the command bar. And then in RFEM, you'll get a status in the lower left-hand corner telling you that the application is locked by connection of an external application, aka Rhino. And then right next to that, you'll get a red abort button as well. And so then you'll see the status pop up in the lower left-hand corner here. And then once you see your model appear in RFEM, the export process is actually complete, even though the status is still here in the bottom left. So all you need to do is click on abort and click yes, and then the export is complete. So you can see here I have my roof layer, my roof surfaces, and my diagonals. And so I could create a model or a structure in RFEM 6 out of this, but I'm not going to show that today. What I do want to show is and talk about are the layer identities, which was the last option that I checked in the export dialog box. So if I go down here into my tables and I go under the tab surfaces here, I can scroll all the way over to the right, and you can see that my surfaces have a roof comment that are my roof surfaces, and then my diagonals have a diagonal comment. So this is beneficial because we can then create user-defined visibilities, or so-called object selection in RFEM 6. So if I go down here to my Views tab, and I click on this button here, Create New Object Selection, this is where we can create object selections. And my first object selection I want to create is going to be for my roof. And then under Surfaces, I want to set my definition to comment, and I want to choose all of these surfaces with the comment roof. Now I can make a copy of this, and I can name this copy diagonals, and then I want to select all the surfaces with the comment diagonals. And so now I have both of those object selections. I can click OK. And now under my visibilities tab here, you can see I have object selection, and I can turn on and off either my diagonals or my roof. So this allows for some customization when it comes to object selection. And so nothing really else to show when it comes to exporting from Rhino to RFEM 6. So now I would just like to show you an import example using a different structure. So I'm going to pull up a different structure in RFEM 6, and you can see here my structure. So side note, I did get this structure from our website. So on our website, we have a page that's called models to download. And on this page, I simply filtered to tensile membrane structures and RFEM 6. And you can download and take a look at any of these structures here. And I encourage you to do so. I chose this one for our example today. So now I'm going to go through and show you how you can import a model back into Rhino. So I'm going to delete my example here. And then I'm going to go up here to my import button. And you can see I have my options here. They look very similar to the export options. I have the option to flip the z-axis, which I'm going to do. And then you also have the option to add in some shift offsets. And then over here on the right-hand side, you can define the layer that you would like to import into. These layers are previously defined in Rhino. So you can choose to import into the current layer, or you can choose to import into a specific layer. For example, let's say I want to import into my roof layer. So now that I have these settings created, I can click OK. And then very quickly, we should see the model pop up in Rhino, like so. And so now you can see that I can click import here, and you can see my model here has popped up here, and I can view all of my lines and all of my surfaces that were created. So now that's basically all of the information and how you can import and export between Rhino and RFEM. So now let's move on to the Grasshopper and RFEM link, which is a little more interesting in my opinion. So I'm going to go up here, and I'm going to open and launch Grasshopper. And so once you have the plugin installed, you should see a new tab up here called the Delubal menu. And with this creates the RFEM 6 components. So these components are placed into 3 different groups here. So the first group here is all about loading. So you can see we have nodal loads, solid loads, line loads, and member loads, etc. And then along with that loading, we have load cases, load combinations, and static analysis settings, etc. So all of the loading needs to be accompanied with load cases and such. So you can see that all organized there. The second category is our model data. So we have basic model data like nodes and lines, along with members. And then every member in RFEM is required to have a material and a section assigned to it. So we have those components here. And then we have our surfaces, and every surface in RFEM requires a thickness to be assigned to it and material. And then we have our nodal supports and all of our other supports. And then just recently added, we have our solid gas component here. So along with form finding, you can create solid gas components as well. So everything is organized in one place here. And now the last category here is our import and export components, and along with our data component and filter component for importing. Let's just take a look at one of our components here. So if I just drag my member component here into my workspace, you can see that we have all of our required inputs here on the left-hand side. And then after filling out the required inputs, we'll get a member that will output on the right-hand side. And you can also see we have a button here to expand the component. And then this will allow us and give us more options. So we have additional options here for defining other elements in our member. And then you can see down here that this component is set to assemble by default. But in case we ever get an RFEM member imported into Grasshopper, we can also set this component to extract. So we can plug in a member and extract this information as well. So now I would like to use some of these components today. And so now then you can get a feeling for the logic and how they work. So I'm just going to delete this component. And to save some time, I'm going to open a predefined example that I have created previously. So you can see here that I have all of my components organized into groups. So this first group here is my Grasshopper geometry. And basically in this first group, this contains the algorithm that creates the structure, which I will show soon. And then I have separate groups here for my RFEM data, following my load combinations and load cases here in my third group. The fourth group here is both of my surface and member loading. And then the last group here contains my final export components. So I don't have time to show all of this today or how to create all of this today, but I will show you the first steps and explain what I have here in this bigger example. So again, regarding the structure, like I said, I have my Grasshopper geometry algorithm here. And with this algorithm, I wanted to create a simple structure with some beams, columns, and a slab on the bottom. And so if I take Grasshopper here and I move it to the right, we can see over here in Rhino, this is the structure that is being created by this algorithm here on the right-hand side. So you can see I have my simple stadium here. And while creating this algorithm, I assigned some parameters that I can use now to modify my structure pretty quickly. So for example, I can modify the amount of frames that I have in my structure here pretty easily. I can modify the length of my stand here, along with the height, the column overlap, the beam overlap, the length of the roof here, and also the amount of bracing that I have in my stand. So you can see that changing, and all of these parameters are based on this geometry. So lots of dimensions have been parameterized, and as a result of this, you get lines at the end here. So if I change my display here, you can see I get my bracing lines, I get my stand supports, my beams, along with my columns and my base plate, etc. So all of these lines are going to be a base for my RFEM model. So all of these lines and surfaces are going to need materials and cross sections assigned to them so they can be exported. So that's what I'm going to show now, basically. So let's say that I want to start modeling an RFEM 6 model in Grasshopper. I have all of my geometry created here. So I'm just going to move this downwards. And let's say we wanted to start with a fresh model. So every model is going to need materials and sections, like I said. Doesn't really matter what this is. What I recommend first creating is a material comp. So let's go up here to my model data, and I'm going to drag down a material component. And you can see with this material component, I have my inputs for it on the left-hand side, and then my output is going to produce a material. And so the three inputs to fill here are not all required, but the first one is we're going to need to define a material number. So this material number can be anything. I can just create a number slider. And this is the material number that is going to be defined in RFEM. And it's not required, so if you don't define a material number, this will be automatically assigned during the export. But I do recommend always assigning an index number for these because it'll help you out a lot in the long run in Grasshopper. So the next bit of information is the material name. So with this, let's say, for example, we want to use the material steel 8992. So you could simply use a text input for this, and I could connect this, and you could enter in the material name, but it's a little bit more complicated because you have to mention the standard as well. So for steel 8992, I would also have to type in the ASC 360, 16, and so this really isn't the best solution when it comes to entering materials. If you have to do a lot of them, this can be tedious. And we've been asked to include a material database, but this really isn't the best idea since we're an international company and we have customers all over the world, which will then include materials from different countries. And so this would be a little more complex. So the best way to do this, we think, is for each user to create their own mini material library, like I did here. You can basically just create a list of the handful of materials that you commonly use throughout your projects. And then you can take this list and you can just copy and paste it throughout all of your projects. And it's pretty simple to do. You can see I just have a list of two materials here, steel 8992 and a concrete material. And so this is, what I recommend doing. And so now what I can do is I can take this list here and I can create a list item component pretty easily, like so. And then if I want to, let's say, choose a material from this list, all I need to do is connect the list here to the first input. And then I can create a number slider and connect that to my index input here. And so let's say I want to choose steel 8992. I can just slide this to 0. And now I'm going to choose steel 8992. And you can see this if I connect a panel here, that steel A992 is being produced out of this list item component. And so now all we need to do is simply just connect this component to our material here. So pretty easy. This is the best solution for creating your materials. And so now anytime you want to create an additional material, this will be our steel material. And I can take this and highlight all of this and make a copy of it, drag it downwards. And now let's say I want my second material here to be a concrete material. I can slide this index number over to 1, and now this will produce a concrete material. So now let's say we want to create some beams. So for a beam, we're going to need a cross section. So I'm going to go up here and grab a cross section component. And so now you could simply just enter well, first we want to create an index number. So every section in RFEM has also an index number assigned to it. And then again, similar to the material, we could just enter a text name for this, or you can create a list like I did for my materials. So here you can see I created a list of different sections here. For this section, for example, we're going to want to use a W21 by 73. So I'm just going to copy my list item component here, bring this downwards, and I'm going to attach my list here into my list component, and then I can simply just set my index slider to 0, and this is going to produce my W21 by 73, and then I can plug this into my section component here for the name. Now in RFEM, like I've mentioned before, a section always needs a material, so that's why you're seeing this material number here again. You can enter in a material by either entering in an index number, so you could take a number slider and connect this to here and just choose the number material that you have, or you can simply link the material directly if you have a number input for these. So we're going to want to change this. So here's our material 2 and material 1, and we're going to want to connect our steel material to our section component here. And so now this section is going to use our steel material, and then the rest of this info isn't really required. We don't need to worry about the angle or the comment. So now we have our section and we have our material, we can create our member component. So I'm going to drag down our member component here. And so you can see, again, the inputs for our member component. This first bit of information is going to be our Grasshopper line input. So our member is going to be based on the lines from Grasshopper that I previously defined. So if I change this, we can take our beam lines here and we can simply hold and shift and drag them into our section component, like so. And now the next bit of information is to assign member numbers. So this isn't required, but I'm going to do it anyway because it's going to help me a lot later on. So I recommend assigning member numbers. To do this, the first option is you could just create a panel like so. And then in this panel, you could define all of your member numbers in a list like so. And then you could connect this to your member, and those will be your member numbers. But the problem when it comes to this is that you're going to need one ID for each line, because from each line we create one member. So we have about 32 lines from our geometry over here. So manually creating 32 list numbers in here isn't really the best idea. And also the bigger issue is that this model is parametric. And so I would have to rework this list every single time my model changes over here whenever I change my model parameters. So the better option is to delete this, and the better option is to use a series component. So I'm going to create a series component here, and with this component, this is going to create a list, and this list should start at 1. So I'm going to create a number slider, and so this is going to start at 1. And then I also have to enter in the step, and so I want the step of this series to also be 1. So now the number is going to, or the series is going to start at 1, and then the next number is going to be 2. And now the next information we have to input into this component is the count. So this is basically how many curves or lines we have, and this component needs to count them. And so we want to create a list connecting the two curves, these two beam components, into this series component. So if I create a panel, a text box, and I connect my beams into this text box, you can see that at the moment, based off of my parameters, I have 35 lines, it looks like. Well, actually, it's 36 lines because this list starts at 0. So we have 36 line curves that we need to take into account for this count here. And so what you can do is create what's called a last item index. And I can connect my beams into this last index or last index component. And so now I will have my 35 lines in here with that list, but it's actually 36 since the list starts at 0. So we need to add 1 to this component. So I'm going to create an addition component, adding 1, and now we can use this as our count for our series here. So now with this count, I can connect this series into my member numbers for my member component. And then just to test, we should see from the series component, if I create a panel here and I connect it, we should see 36 lines that are, or 36 lines that are counted here. So you can see at the bottom of my list here, there's 36, so perfect. We can use this for our count. And now this, I know this looks difficult, but it's really not too bad when you get it down. And the benefit of this is it's parametric. So when I change the number of frames in my model over here, the list for the members is going to, for the member numbers is also going to change. So I don't have to worry about that. Now the rest of the information in our member component. So we have the member distribution that we need to assign. So we can set this using a value list. So I'm going to create a value list and connect this to my distribution here. And so you see we have a list of member distributions we can choose from. I'm going to choose uniform. And then the section start. So we need to define our section start, which is going to be our cross section. So you can assign the section start using a number slider, or you can also define the, if you've defined the section number up here in the section component, then we can simply take this component and connect this to the section start. But that's only if you have assigned a section number to the section component. So now that the next bit of information is the section end. This is only really useful if we've defined a linear section distribution, then the member type. So this is also controlled by a value list, so I can just connect that. And you can see in this value list here, we have a long list of different member types. So we have beam, compression, rigid, tension only, truss. So I'm just going to keep this set to beam. And now we have a little bit of additional options here. So we can choose a rotation type. And this was highly requested. Before, you could only change the rotation based on a rotation angle, but now it can also be related to a specific node. And I do use this in the larger example above, so I'll show you how this works later on. But then you can also define hinges and eccentricities as well. So that's everything regarding the member component. And now let's move on to the surface component. So I'm going to go up here and I'm going to drag down a surface component. So the surface component is also based on Grasshopper surfaces. So we can connect the Grasshopper surface that I created into the first input here. So I'm going to move over here and take my bottom plate lines, and I'm going to move it over. Let's move my component a little closer and connect it. And so now we have our Grasshopper surface used as our base for our surface component. Next, we want to create an index number. So this can just be 1, and I'm going to plug that in. And then we just need to define the thickness number. So material and thicknesses aren't defined directly onto a surface. We have to assign a thickness number or a thickness component to the surface. So I'm going to go up here and create a thickness component. So with this thickness component, we first need to define a number. And I did want to mention this logic for assigning a thickness to a surface comes from RFEM. So if I go back here to RFEM and I create a surface, you can see every surface here has to have a thickness and material assigned to it, and each of these has their own index number applied to it. So back to Rhino, we can create a number for this thickness component and assign that. And then we also have to create a material number. So we can go up here to our concrete material, and I can drag and connect my concrete material to my thickness material down here. So now I'm using my concrete material. And now we need to control what the actual thickness of the surface is going to be. Now, very important to know, all of the components in Grasshopper are using SI units. So something like this thickness unit here is referencing meters. So what we need to do, and what I recommend, is if you're using imperial units, is to create some conversion components. So for example, I could create this conversion component and name it inches to meters. And then to convert inches to meters, I would have to divide by a constant of 39.37 and connect this. And then let's say I want this surface thickness for this concrete to be 8 inches. I can simply just create this slider, set it to 8, and then I can simply connect this component into my thickness here. And now I'm going to have an 8-inch thick surface. And so then you can simply just create a blank file with all of these conversion components, and you can just make copies of them and plug them into anything that you need to, for example. So that's the workflow I recommend for converting. And also we can add a comment, that's optional. And so then all we need to do is take this thickness component and plug it into our surface component up here. And so now our surface has a thickness assigned to it. We also have some more options here. So we have stiffness type, which you can assign. And then also there's the ability to add in or to define the surface based on lines and geometry type. So surfaces are based on, right now my surface is based on Grasshopper geometry, but you can also base a surface on boundary lines and geometry type in Grasshopper if you'd like. And so with that, now we want to create some supports. So when it comes to supports in Grasshopper, we have a couple of different options. We have nodal supports, we have line supports, and then we also have surface supports. So we integrated a lot of features into the nodal supports component here. So if I click on more down here, you can see that you can now base a support on a specific angle, and you can also base support according to a specific direction, as well as a specific plane and specific node as well. So I'm going to focus on my surface support here. So I'm going to delete my node and line support. And with this, we need to give it a number, and then we need to assign a surface number to it. So I can just simply take my surface component and plug that into the surface number input here. And then we need to define the translation degrees of freedom, X, Y, and Z. And you can see when I hover my mouse over one of them, I get a comment that tells me how to define them. So you can see you can create spring constants. And again, this is according to SI units. So that would be Newton per cubic meters. I recommend creating a conversion component for that if you're assigning that. And then the other two options, if you want to fully release this degree of freedom, you would enter in 0. And if you want to fully fix a degree of freedom, you enter in IF or infinite. So for these 3 degrees of freedom, X, Y, and Z, I'm going to enter in INF and hold shift, and I'm going to make sure all 3 of these are fully fixed. And so, yeah, so now we have our surface support assigned to our surface. And so far regarding the model data, that's basically how you can start. And we can go up here to my larger example, and we can see in my larger example up here how I define my model data. So you can see I have all of my materials right here, and then I have all of my sections defined as well. And with these sections and materials, you can see they all connect and help define my members over here on the right-hand side. So I have my main beams, I have my columns, my grandstand bracing, my supports, cables. You can see my cables are set to tension only, and my joists are set to truss. And so this is what I have defined here. You can also see for my columns here, I'm utilizing our new feature, the help node, and you can see I'm referencing the rotation plane XZ of the member, which is the strong axis of my columns. And so then I'm using some help nodes up here. So if I go back down to my geometry here, you can see over on the right-hand side in Rhino, these green nodes that all line up with my columns are what I'm using for my help nodes. And then if I click on, you can see for my columns, these are all the columns that I'm referencing. And so now the strong axes of my columns are going to be in the correct rotation, no matter even if they're going along this curve here, because I'm referencing these help nodes. So that is the benefit of using help nodes and your model data here. And then at the bottom here, you can see, lastly, I have my thicknesses and my surfaces along with my surface supports. So that's all I have and defined in my RFM model data here. And so the next thing to move on to, or the next aspect to move on to, is creating load cases. So I can create a load case comp up here, and I can drag that down here. We can see with my load case comp, I can assign a number, and then I can also assign a name. So I'm going to name this load case dead load, and I can simply just connect that into the name. And then the next bit of information is the static analysis settings. So static analysis settings is something we also have to define in Grasshopper, and this follows the logic in RFEM 6. So if we go back to RFEM 6 and I create a new load case here, you can see that a load case has to have a static analysis setting. And by default, this is set to geometrically linear for load cases. So what we need to do in Grasshopper is to go up here to our static analysis setting comp and give this a number as well. So I'm going to assign that, and we're going to make that number 1. And then under the static analysis setting comp, we need to give it an analysis type. So we can use a value list here to do that. So I can connect to my value list, and we can choose geometrically linear from this list. And then the next option is exceptional handling, which is for structures that have a lot of tension-only members and tend to fail under vertical loading situations, causing instabilities. And so this option can be turned on using a Boolean toggle. So if I create a Boolean toggle, I can connect that. And whenever this is set to true, we're using that option. And when it's set to false, that option is turned off. So now I can connect this to my load case. And then the next information to assign is the action category. And this action category is linked to the code that you're using. So for example, if you're using the ASC 7, for example, this is going to be defined in the base data back in RFM, which you can see under standards here. So I'm using the ASC 7 for this example. Back in Rhino, we can create that comp to create action categories. So this is the action category component, and this is where we can define our standard. So we can choose the ASC 7. I can move this over, and then since I chose the ASC 7, then we'll get different action categories depending on the standard that you choose. So I'm just going to choose dead load and assign this action category to my load cases. And you'll also get different design type situations, or design situations, which we'll go over in a little bit, depending on the standards you choose. And so that's how you can define your action category. And then back under the load case comp here, we can click on more and we have additional settings here. So we can activate self-weight here using a Boolean toggle. So I'm going to connect that and set that to true. So for our deadload case, we have self-weight activated. And by default, this references the global Z direction and is set to a -1 factor. And so now what I can do is I can take these components and Control C and Control V them. And I'm actually going to move over all of these just so we have a little bit more space. And so with the second load case here, I can create my live load. And then I'm going to change the name here to live load, click OK, and then turn my self-weight off. And then I want to choose the ASC7 and I'm going to choose live load. So now I have my first load case and my second load case. And now we need to go over load combinations. So when it comes to load combinations, I can just drag down here a load combination component, and we need to define a number, or actually the load case number or the index number for load combinations isn't really too important because we don't use load combinations anywhere else in our information here. So it's not too important to reference. The combination name is also not too important. What we really need to focus on immediately is the design situation. So every combination in RFEM is linked to a design situation. So if I go back to RFEM and I go to my load combinations, we can see, or you can see if I have some design situations here, and I have ASD and my LRFD design situations, and I create some load combinations. A load combination is always needs to be assigned to a design situation, whether that's LRFD or ASD, and it also needs to have a static analysis setting assigned to it. And so we need to create a design situation first. So I'm going to go up here and drag down my design situation component. And so now with this design situation component, I'm going to assign a number to it. So it's going to be number 1. Again, name's not too important. Let's say this design situation is for our LRFD design situation, or load combinations. And then we need to define a type. So for the type, we can then create an action category or a design situation type using this load case classification component. So I want this to be according to the ASC7. And then I want my design situation type to be LRFD. So I'm going to move this over. And then we can connect this to our design situation component. And with this design situation component now, we can connect this to our load combination component down here for design situation. And now we have that assigned. We can also create another static analysis setting component by control and copying this over here. And so then we can set our load combinations to a second order analysis setting, connect this to our load combination component down here. And now the last information we need to assign is the items. So this is important because we need to define which load cases and factors we will be using for the combination. So what we can do here is first we need to create a load combination load combination items component by typing that in and getting our load combination items component here. And with this one, we have to define the load case numbers and then the factors. So we can easily just create a panel, a text panel here, set this to multi-line data, and then type, so we're going to be using or referencing our load case 1 and load case 2. So we can connect that into our load case number. And then we need the corresponding factors. So again, we can create a panel here and enter in our factors. So let's say for our first load case, we just want that to be have a factor of 1.35. And then our second load case will have a factor of 1.5. And then we can plug this into our load combination items component. And so it'll take that information and then we can plug it into our load combination for our items. So that's how you can create load cases and load combinations. And we again, we can go over this in my larger example up here. So up here, you can see I have both my static analysis settings activated, and then I have my action categories for my load cases on the right-hand side here. And then down here, we have our design situation classifications for LRFD and ASD. And then you can see here, I created two categories for my LRFD combinations for my load cases and my ASD combinations. So with these text panels, I'm basically just combining multiple panels for multiple load combinations. And then I'm using this entwine component to combine all of them. And then the same thing down here, I have my factors that are going to correspond to those load cases up here. And then I combine them. And then again, I'm using my load combination items component and then plugging that into my load combination component. And doing this basically just saves you time from having to create multiple or a lot of load combination components here. And you can also use text boxes to assign the design situations as well. So that is how you can create load combinations. Lastly, the last bit of information we need to go through is how to create loads. So we have our loads up here. We have nodal loads, we have our line loads, member loads, etc. And we can create, let's say we want to create a member load component. And so with this, again, for this one, it's actually optional to define an index number, but we do need to assign a load case number. So basically I can just take one of my load cases here, like my live load, and assign that to my member component. And then we also need to assign member numbers. And so this is why it's good to assign numbers to members, because then we can just simply take our member load component here and we can connect it to our member load component. We can take our member component here, since we assigned those member numbers, and connect it to our loading component here. And so now we don't have to worry about assigning member numbers to this, which keeps it pretty easy. Then we need to assign a load type, and this is controlled by a value list. So I can plug in my value list here, and you can see we have a bunch of different load types. I'm going to choose the load type force. Then the load distribution is also controlled by a value list. And you can see here we have a list of different load distributions. I'm going to choose uniform. And then our coordinate system, I'm going to choose the local coordinate system, which is set to 1, or you set 1 for the local coordinate system. And then the load distribution also is controlled by a value list. So I can connect that, and I want to choose the global true Z direction for the distribution. And then lastly is the load magnitude, which again, you can see is newtons per meter. So keep that in mind. If you want to create a conversion component for this, you can simply create a multiplication component like this, and then you can name it something like pound per foot to newtons per meter. And let's say we want to have this loading be 1,000 pounds per feet. So I'll just type that in there. And then to convert from pound to foot to newton per meter, it would have to be a constant of 1.36, like that. And we can connect that, and then we can connect that to our magnitude here. So again, you can take these, create them, and then save them and use them whenever you need to in a separate file. So now that we have all of our components created, we can create the export component. So we can go up here to our export component and create it and drag it down into our workspace. And the first information here is the run input, and we can create a button component to connect to this. And so now every time we press this button, it will activate the export. The other option for this is you could use a Boolean toggle and connect this instead. And then every time you have this set to false or to true, anything you change within Grasshopper will change in RFEM, and this will be a live feed. So you could see things update live in RFEM while you're changing and creating data in Grasshopper. So I'm just going to choose or stay with the button. And then with this component, we have the input data. So everything that we want to export has to be connected to this input. So I'm going to hold Shift down, and we have to connect our member load here. We also have to connect our load combination component and our static analysis settings. So all of this has to be connected, our design situation, and our load cases, they also have to be connected. So we'll connect our load cases like so, along with our other static analysis setting here. I'm going to change my display. And then we also need to connect things like our surface support here, along with our surface itself, and our member, and our section. And then our materials need to be connected as well to this component. So we'll connect all of our materials to that input, and our thickness also has to be connected to here as well. And so yeah, all of that needs to be connected like that. And once you have that connected, then you can also go through some additional options when it comes to the export. So we can also click on additional here. And so we can also control the units via a value list. Now this is only the units for the dimensions of the actual geometry. So you can control that here and how that's exported into RFEM. You can also flip the z-axis using a Boolean toggle. So you can flip the z-axis if you'd like as well. Tolerances, I really wouldn't worry about tolerances too much. And I would only worry about tolerances if you have nodes that are very close together and they become merged in RFEM during the export. And what you can do is back in the settings in Rhino here is you can go up to tools and options, and then under units here, you can also change the tolerances here in Rhino. So that's how you can modify the settings there. Also with the Boolean toggle, you can choose to, if you want to overwrite the data in RFEM or not. So if this is set to true, every export will overwrite the existing data. And if this is set to false, this will add new data to an existing RFEM file. So basically we have the option to modify an RFEM file because you have to assign IDs if you assign IDs to every component in your Grasshopper file, then only those components will be modified. So for example, with an ID for a member, if I want to change a single member with an ID, I can do that pretty easily and modify a file in RFEM. So now we could start the export. I'm actually going to just export this larger model up here, which you can see is about the same. So I'm going to move Grasshopper over, and then all I need to do is click the button here on my export. And then you can see the status down here, and RFEM will change, again, telling me the application is locked by a connection of an external application. And it'll show me the abort button on the right-hand side. And then, like I said, once you see the model appear in the graphical window, that means that the export is finished, and then you can abort, and you can then finish up looking at the model in RFEM. So this should only take about a minute or so. It should be pretty quickly. And then, like I said, once the model appears in RFEM, then you can hit the board button and the export should be finished. And so let's try hitting abort and trying this one more time. And you can also see in my Grasshopper example here, I have all of my inputs connected. So everything should be working properly. And all of my geometry is defined. And so what I can do is click abort. And we can go back here. And then there we go. So now, looks like I was just zoomed in too close. We have the geometry all defined here and the model imported. And up at the top here, you can see I have all of my flow cases defined along with my load combinations and design situations. All of my materials are imported along with my sections and thicknesses and surfaces. And yeah, so this is how you can import in a Grasshopper model into RFEM 6. And you can also, last thing I wanted to show was the loading as well. So all of my loading is properly applied here. And so the last thing I want to do is now I'm going to hop back to the PowerPoint. And the last slide I wanted to go over, and the last bit of information before handing the reins back off to Amy, is some future developments. So we do have some future developments, more short-term developments that should be implemented actually pretty soon, is we've created a component that allows you to apply loads to the perimeter of an opening in a surface. So that component should be added pretty soon into Grasshopper and is pretty useful for adding, like I said, loads to the perimeters of opening and surfaces. And then we're also adding the option to be able to rotate lines using a help node. So this is similar to what I did back in my example with members, but now this option will also be, you'll also be able to use this with lines as well. And then some more long-term future development goals. I mean, in general, we strive to extend / add new features related to just models, our model and load data in general. We also wanted to add in the feature to be able to start the calculation in RFEM 6 via Grasshopper. And along with this, we wanted to be able to also read the RFEM 6 results back into Grasshopper when you are importing back from RFEM into Grasshopper. And then lastly, we want to add in the ability to display the outlines of members when it comes to importing in members from RFEM 6 back into Rhino / Grasshopper. Currently, we can only show the lines. So this is something that one of our goals to do. And with that said, I'd like to hand back the reins to Amy so she can conclude the webinar for today.
Perfect. Thanks, Alex. So we know that's quite a bit of information. We did record this presentation today and we will put it up on our website. You can find that recording along with the PowerPoint and additional Rhino and Grasshopper models on the same webpage that you registered for this webinar. We will have many more upcoming webinars. You can also download a free 90-day trial version on our website to test out this integration with Rhino and Grasshopper. And if you have any questions about today's presentation, feel free to reach out to us in our Philadelphia office. You can see the contact information in the lower left-hand corner. Our phone number is 267-702-2815, and our email directly to our Philadelphia office is info-us@deluwald.com. We will have additional webinars coming up. You can register at deluwald.com under support and learning webinars. And most of you know I tend to send out a reminder email about a week before these take place. So just keep an eye out for those. PDH certificates will automatically be emailed to all participants who were here for the full presentation. That is a requirement from the states that we are pre-approved providers, that you are here for the full duration of this webinar in order to receive that PDH. So you can expect to receive that through the email that you registered for the GoToWebinar. If you did watch the webinar with a colleague or in a conference type setting and you yourself did not register for the webinar, feel free to send us an email at info-us@deluwald.com. Again, info-us@deluwald.com in order to request that PDH. And with that said, we want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.